So, today let us look at Pauli spin matrices, and so we have seen the definition of linear vector space. Okay, and see any vectors. So, the concept of vectors is any quantities basically. Okay, which satisfies whatever the conditions I have written earlier. Then we call those things are basically the vectors, and we can also have basis vectors in that, which satisfies two conditions basically: the linear independence of the vectors in that basis vectors, and they span all the space. So, so now let us look at space of 2 by 2 matrices. Okay, the space of 2 by 2 matrices. Let us see the matrices sigma 1, which is equal to 0 1 1 0, and sigma 2, which is equal to 0 I minus I 0, and sigma 3, which is equal to 1 0 0 minus 1. Okay. So, this is minus 1. So, these three matrices are called spin matrices or Pauli spin matrices. They are very useful when you talk about the electrons, okay, and their representations. So, now let us look at see. Now, if I take any 2 by 2 matrix A, B, C, D, any general 2 by 2 matrices. Okay. Now, can I write this 2 by 2 matrix in terms of these three matrices? Is it possible? That is the question. Okay. Can I take any 2 by 2 matrix and write it in terms of the Pauli spin matrices? Is it possible?
If it's traceless, then
yeah.
If it's traceless, then we can.
If it is traceless, so what do you mean by see? Let us look at. So suppose I want to write any 2 by 2 matrix in terms of sigma 1, sigma 2, sigma 3. Okay. Suppose I want to do that. So that means you take any general matrix. Any general matrix A, B, C, D, so that I should be able to write that general matrix in terms of sigma 1, sigma 2, sigma 3. That means some alpha 1, sigma 1 plus alpha 2, sigma 2 plus alpha 3, sigma 3. Okay. So now if I do this, suppose I add this, multiply some number. This number can be any number in general, can be complex also. Okay. So if I do that, so what is alpha 1 sigma 1? Alpha 1 sigma 1 is so alpha 1 sigma 1 is 0 alpha 1 0 plus alpha 2 sigma 2 is 0 minus I alpha 2 I alpha 2 0. Plus alpha 3 sigma 3 is alpha 3 0 0 minus 1. So what is this sum equal to? So what you are going to get is
minus alpha 3.
Minus alpha 3, yes, minus alpha 3. So if I sum this, what I am going to get? 0 0 and alpha 3. So the first one is alpha 3. Then alpha 1 minus I alpha 2 then alpha 1 plus I alpha 2, then minus alpha 3. Okay. So, I am trying to write any general 2 by 2 matrix in terms of sigma 1, sigma 2, sigma 3. So, if that is the case, so I need, so alpha 3 and minus alpha 3 are in general complex numbers, right. So, can I find alpha 1, alpha 2, alpha 3, okay, in such a way that I can uniquely find out A, B, C, D in terms of, can I find now? Can I uniquely write down A, B, C, D in terms of alpha 1, alpha 2, alpha 3? Is it possible? For any general A, B, C, D. So, if you equate now, what are you going to get? If you equate this one matrix with this matrix, you are going to get A is equal to alpha 3 and B is equal to alpha 1 minus I alpha 2 and C is equal to alpha 1 plus I alpha 2 and D is equal to minus alpha 3. Okay. So, this is what I get if I equate this matrix with this matrix. Is there any problem with this?
Yes, sir.
So, what is the problem?
Sir, we can only define matrices if A is equal to minus D. If
A is
they
so,
are not equal,
yeah, if A is equal to minus D, okay, so only such matrices I can write like this, okay. So that is one drawback you can see. So, you cannot any general 2 by 2 matrix you cannot write in terms of sigma 1, sigma 2 and sigma 3, okay. So, see, in general this 2 by 2 matrix, how many quantities are there? How many quantities are there in a 2 by 2 matrix? How many real quantities are there? Yes? How many real quantities are there in this matrix?
Two real quantities.
sir, are you asking for general or
General. I am asking for general a matrix A, B, C, D, okay, 2 by 2 matrix, any general complex.
four quantities will be there, sir.
Only 4 real quantities? There are 8 real quantities, okay. So, each one is a complex number, okay. Each one of them is a complex number. So, obviously, 2 real quantities here, 2 real quantities here, 2, 2. So, there are 8 real quantities are there, okay. So, when I write alpha 1, alpha 2, alpha 3, so in general I can have a complex numbers, right. So, alpha 1, alpha 2, alpha 3 can be in general complex numbers. So, how many quantities I can get it from there? I can get only 6. So, 2 are, so you cannot, that way itself you can see that you cannot write in terms of sigma 1, sigma 2, sigma 3, okay. So, some special matrices can be written such a way. So, what to do? So, I can also include the identity matrix which is 1, 0, 0, 1, okay. If I include the identity matrix in this, then I can write down any 2 by 2 matrix in terms of these 4 matrices, okay. So, if you give me any 4 matrices, okay, any 2 by 2 matrix I will be able to write it in those terms, okay, that is not at all an issue, okay. So, sigma 1, sigma 2, sigma 3 and I form a basis for a any general 2 by 2 complex matrix, okay. And so one condition only we said here, right, that is it actually span all the space of 2 by 2 matrices, but are they independent? Okay, whether these 4 matrices are independent, can I write one of them in terms of other 3? Is that possible? So, that condition also should be satisfied if you want to have those 4 to have a basis to satisfy the basis set condition, right. So, can I write any of these matrices in terms of other 3 matrices? Yes, yes.
Sir, can you explain again how they can span all the 2 by 2?
Okay, so now I write down. Yeah, so we have I also there. So let me write down. So take any matrix A, B, C, D. Now I am writing down, that is alpha 0 I plus alpha 1 sigma 1 plus alpha 2 sigma 2 plus alpha 3 sigma 3. Okay. So I am writing like this. So now we continue whatever we have done earlier. Okay. So if you do that, so let me just write down this sum. So this will be identity matrix, means alpha 0 0 0 alpha 0 plus alpha 1 0 alpha 1 alpha 1 0 plus 0 minus I alpha 2 0 plus what is next, alpha 3 0 0 minus alpha 3, right. If I add these 4 matrices, what I am going to get? So I get alpha 0 plus alpha 3, then alpha 1 minus I alpha 2, right. Then alpha 1 plus I alpha 2, then alpha 0 minus alpha 3. Is that all right?
Yes, sir.
Okay. So I got that. So now I can write down A is equal to alpha 0 plus alpha 3 and B is equal to alpha 1 minus I alpha 2 and C is equal to alpha 1 plus I alpha 2 and D equal to alpha 0 minus alpha 3. So I can solve A and C. Okay. So I can find out. Alpha 0 and alpha 3 in terms of A and D. So what is alpha 0 equal to? What is alpha 0?
D by 2.
A plus D by 2.
2.
Then alpha 1, what is alpha 1 is equal to? So alpha 1 I can write it in terms of, so if I solve sum these two, right. So B plus C by 2 will be alpha 1. Then what is alpha 2?
C minus B by 2i.
C minus B by 2i. Then what is finally alpha 3 equal to? This and this.
A minus D by 2. A minus D by 2.
A minus D by 2. So for a given general matrix, any general matrix, okay, I can uniquely find out alpha 0, alpha 1, alpha 2, alpha 3. Okay, but they are the coefficients of the vectors I, sigma 1, sigma 2 and sigma 3 respectively. Okay. So you give me any general 2 by 2 matrix, I now can expand in terms of these 4. That is what you mean by it spans all the space. So that is clear, right? Now you take any of this matrix. Is it possible to write it in terms of other 3 matrices, or if I write summation AI, because sigma I Okay, so that is for I is equal to 1 to 3 plus then identity also some A0 identity equal to 0. Okay, suppose I write like this. Can I find out a non-zero A's, okay, A0, A1 or A2 or A3 such a way that this equation is satisfied? Or can I write any matrix, any of these matrices in terms of other three matrices? Is it possible? It is not possible. Do you want me to do that or will you try that?
What you said, please repeat it again.
So because if you want some set of vectors as a basis vectors, what you want? Two conditions. One is it should span all the space. That we already seen. Any 2 by 2 matrix, you can write it in terms of these 4 matrices. Second condition, those vectors should be linearly independent. So can I write down either I can find out non-zero A's from which satisfies this equation, or that is same as can I write down any of these metrics, sigma 1 or sigma 2 or sigma 3 or I, in terms of other three matrices. Okay. So can I write down 1 0 0 1 in terms of these three? It is not possible. Okay. I cannot write down 1 0 0 1 in terms of these three, because see, if you look at 1 0 0 1, so this one is having 1 and minus 1, right? So I cannot write down 1 0 0 1 in terms of this one, because these are only having this matrix only having the diagonal elements. They are actually opposite, but what you are having is a 1 1. So obviously you cannot write down. Okay. Similarly, you can actually solve this in general. Okay. So thus yeah.
In that case, they cannot form the basis, right?
No, they are linearly independent. Okay. So because basis means they should be linearly independent. That's what we are showing now. Okay. If they are linearly dependent, obviously, so if they are linearly dependent, then it is not a basis. Okay. So if you can write one in terms of other thing, means they are linearly dependent. Okay. So we cannot write in terms of those. Okay. So what is the trace of all these matrices? So let me write down these matrices. So here, so that you can see what is the sigma 1? 0 1 1 0. What is sigma 2?
0
0 minus I 0. And what is sigma? What is sigma 3 is 1 0 0 minus 1, and identity matrix is 1 0 0 1. Again, this is not traceless. All other things are traceless. Trace is 0, trace is 0, trace is 0 here. Okay.
Yes.
And what is the determinant of each of these matrices? What is the determinant of each of these matrices?
Plus minus 1.
Determinant is minus 1. So trace is 0, determinant is minus 1, a 2 by 2 matrices. So what should be the eigenvalue?
Then that will be plus minus 1.
Plus minus 1, because trace is the sum of the eigenvalue. So some of you may not be knowing what is an eigenvalue for a matrix. So any n by n matrix you take A. Okay. So what are is I am not getting into the general theory for only for our doing certain things here, because your mathematics, because BTech students, your maths course will cover a big topic on this, and other PhD students already you have done all those things. But so just have we want to find out the eigenvalues of these matrices. Okay. So for that purpose I am now doing. So if I have matrix A, what do you mean by eigenvalue equation? Okay. So there is a matrix A into some vector. So you say vector u, okay, which is equal to lambda u. Okay. So this is basically a column matrix. Okay. So if I have matrix 2 by 2 matrix, I write down like this A, B, C, D. Then this u vector is nothing but some unknown, okay, x, y. If that gives this matrix into that unknown column matrix gives some lambda, which is the eigenvalue x, y. Okay. So if you are able to find out this lambda and this eigenvalues, so the eigenvector. So this is an eigenvector. Okay. So in general, for a 2 by 2 matrix, if determinant is not equal to 0, there will be 2 eigenvalues and correspondingly 2 eigenvectors will be there. Okay. So how will you find out eigenvalues of a matrix? So to do that, because you can take this minus this one equal to 0. So basically if you take the determinant of A minus lambda I equal to 0, you can actually, this will give you a characteristic equation. So what is a characteristic equation? If I suppose it is a minus lambda I, so 2 by 2 matrix, what will be the characteristic equation? So if I just write down 2 by 2 matrix as A, B, C, D. So A minus lambda I, where I is the identity matrix. Okay. So A minus, what will be here? Lambda. So I want to find the determinant, right? So A minus lambda I determinant. Okay. So A minus lambda. So next one is B. This is C. This will be D minus lambda. So this is a matrix. A minus lambda I is a matrix. Then you have to find the determinant of that. Okay. So that will give you a characteristic equation. So what is the equation you are going to get here? So you will get a minus lambda into D minus lambda minus BC equal to 0. So for a n by n matrix, so now you think about A is a 3 by 3 matrix. If A is a 3 by 3 matrix, because here you can see that what is the order of the polynomial here, the lambda is a polynomial in lambda, right? So what is the order of the polynomial? Square, 2, right? So this is a 2. Basically it will give you a quadratic equation, right? It will give you a quadratic equation. So you have to solve this quadratic equation to find out, because for a quadratic equation you will have 2 solutions. So you can find out lambda 1 and lambda 2. So if I take A is 3 by 3 matrix, so this will be A minus lambda, some D minus lambda, something here, okay, E minus lambda. So if you find the determinant, that will be you get an equation that will be because polynomial, okay, in lambda, that will be the polynomial of the order 3. Fine. So you get 3 eigenvalues. So in general, any n by n matrix, okay, if you solve the characteristic equation, you get n eigenvalues. So if I get the eigenvalues, so what you can do is, for example, 2 by 2 matrix, you substitute lambda here, because by solving the characteristic equation, you can find out lambda 1 and lambda 2 for a 2 by 2 matrix. So you substitute that lambda 1 here and lambda 2 here, then actually you can solve. So this you can actually write down, because ax plus by is equal to, if you substitute lambda, suppose lambda is 1, you get x, then cx plus dy is equal to some y. So if you solve that equation, you get x and y, right? That will be a linear equation. The determinant of this is not 0, that's what, because in general we can actually solve. Okay, there are certain cases you may not be able to find out. Anyway, those theory you will learn later. Okay, so here, so for each lambda you can get one set of xy. So that is a vector. So that is the eigenvector. So one xy for a given lambda will give you one eigenvector. For another lambda you get another eigenvector. So you get 2 eigenvalues and 2 eigenvectors for a 2 by 2 matrix. Okay, in general. So now let us look at this Pauli's spin matrices. Let us find out its eigenvalues and eigenvectors. So 0, 1, 1, 0. So what is the characteristic equation for this? So I have to write down minus lambda 1, 1 minus lambda equal to 0. So what you have to do is A minus lambda I. This is the identity matrix. Okay. So determine that equal to 0. So basically I have to subtract lambda from the diagonal elements. That's all you have to do. Okay. So minus lambda 1, 1 minus lambda equal to 0. So this, what is the characteristic equation corresponding to this? Minus lambda into minus lambda, lambda square minus 1 equal to 0. So what are the solution? Lambda is equal to plus or minus 1. Okay. So this is what somebody earlier said, you get eigenvalues plus or minus 1. So in general, if you take any matrix, the eigenvalues, the trace will be the sum of the eigenvalues. Trace will be equal to sum of the eigenvalues. And the determinant will be equal to the product of eigenvalues. So you can see that in this case the determinant is minus 1, right? So determinant of this matrix is minus 1. So the product of eigenvalues, lambda 1 is plus 1 and lambda 2 is minus 1. So product is minus 1. And the sum of the eigenvalues plus 1 plus minus 1, 0. So with that understanding, when you find out the eigenvalues and eigenvectors, you can actually cross check what you are getting is correct or not. So now I got two eigenvalues plus and minus 1 for sigma 1. So all of you, can you quickly tell me what is the eigenvalues and eigenvectors for sigma 2 and sigma 3? Quickly do that and give me the answer for sigma 2 and sigma 3 eigenvalues. Okay, so for other matrices sigma 2 and sigma 3 you got eigenvalues same as plus or minus 1, and for this identity matrix what you got was both eigenvalues are same, which is equal to 1. Now most of you have already found the eigenvectors of sigma 1, sigma 2. I just do it for sigma 1, how to find out the eigenvector for the matrices. So you have sigma 1, that is 0, 1, 1, 0. Then write down xy. Then you have lambda 1 is equal to plus 1 and lambda 2 is equal to minus 1. So this is equal to, first take lambda 1 is equal to plus 1. So that is plus 1. Okay, so 1 into xy. So our job is to find out the x and y. So you get 0 plus y, y is equal to x, x is equal to y. So you can actually choose any x and y. So this is your freedom. Okay. So but if you normalize, things will come to one unique one. Okay. So I can choose x is equal to 1. So y is also 1. So in this case, what I am going to get is 1, 1 as the eigenvector corresponding to lambda 1 is equal to plus 1. If I normalize this eigenvector, what I am going to get? 1 by root 2 into 1, 1, right? So this is a normalized eigenvector. So if I take this one, that is sigma 1 into this one, I will get 1 into this one itself. That you can just verify. Okay. So you just put 1, 1. Don't put lambda, what is lambda? Okay, you can actually automatically get that. So what is this equal to? Okay, with a normalization condition. Okay, so this is equal to 0 into 1, 0, 1 into 1, 1. So 1 and 1 into 1, 1. So 1. So this 1 by root 2. So you can see that this matrix acting on this one giving you the same 1, 1, right? So the eigenvalue is what is in front of that. 1 by root 2 is already there. So 1. So for lambda 2, you have to again write down xy. The eigenvalue is minus 1. Then xy So what are you going to get is y is equal to minus x and x is equal to minus 1. So now you can see, you can either choose x is equal to 1, then y is equal to minus 1. Okay. So if you normalize that, what are you going to get is 1 by root 2, 1 minus 1. Okay. So there are two eigenvalues, plus 1 and minus 1, and those eigenvalues are have the corresponding eigenvector 1 and 1 minus 1 respectively. So similarly you can do it for other matrices, okay, that I give it to you as an exercise. So this is very important because you will come across these matrices, these Pauli matrices later on when you talk about electron spin, okay. So how to expand the spin angular momentum, okay, in terms of certain basis and all. So that point you will come across this Pauli matrices. We can do a lot with the Pauli matrices now. Let us what is sigma 1 sigma 2 equal to? What is sigma 1 sigma 2? Okay, let us don't worry about sigma 1 sigma 2. What is sigma 1 square? Quickly you can give me the answer. The square of this matrix, first matrix.
Sir,
Yeah. Yes? Can you hear me?
sir, hello. Am I audible, sir?
Yes, yes, yes.
Hello. Sir, class 1.
Identity matrix. Okay. What is sigma 2 square? That is also identity matrix. So sigma 3 square is also identity matrix. Okay. So what is sigma 1 sigma 2? You can easily multiply. What is sigma 1 into sigma 2? Is it sigma 3?
Sigma 3
I sigma 3. Okay. So what is sigma 2 sigma 1?
Minus I sigma 3.
Minus I sigma 3. Okay. So now I will give you this as an exercise. Okay. So in general, what is sigma I sigma j equal to? So sigma j, can anybody tell me what is sigma I sigma j equal to for any I and j? Because you have some understanding now. Okay. Sigma k?
I sigma k.
I sigma k. Is it correct?
For cyclic permutation.
If you want a cyclic permutation, what should I put here? Epsilon.
And j.
Because when you write, there is something wrong now, because I and j are free index. K is a free index. So that is not correct, right? So there should be I and j should be appearing the right hand side also. Okay. And so when I write sigma I sigma j, so obviously so I j k. Okay. So k is summed over. So you get I j k I epsilon I j k sigma k. But is this correct? Again my question. This up to certain level it is correct, but not completely correct. Anybody can point out?
Plus del ij.
Yeah, so you have to tell me the reason, because I and j can be also 1 and 1, right? I can be 1, j can be 1. Okay. If I is 1, j is equal to 1, according to this equation it is 0. But that is not. Sigma 1 square is delta means identity, right? So plus delta ij identity matrix. Okay. So sigma j is iota epsilon ijk sigma k plus delta iji. When I and j are same, you get identity matrix. If they are different, you get the third matrix, and the sign depends on whether it is a cyclic permutation or not. So if you do not understand this, you just go and do it. Okay, so you will get the idea. Okay. So what is the commutator of? So what do you mean by commutator? Suppose I have a two matrices A and B. The commutator of these two matrices is basically equal to AB minus BA. So when I ask whether the matrices, any general two matrices A and B commutes with each other. Commutes with each other means this quantity equal to 0. So whether any general 2 by 2 matrices, they commutes each other.
No, sir.
The answer is no. So any general two matrices will not commute each other because AB is not equal to BA. Fine. So then can you give me the answer for sigma I, sigma j? What will be this answer equal to? So commutator you know how to find out. You find out AB and subtract BA from that. Okay. So what will be sigma I, sigma j? Commutator of sigma I with the sigma j?
0.
0?
Yes, sir, 0.
No, sir. 2 times
2
the
and
first one.
2 times?
I epsilon I get sigma b.
See, if I and j are same, okay, if I is 1, j is 1, sigma 1 commutes with any matrix, commutes with itself, okay. So sigma 1 commutes with the sigma 1, but sigma 1 does not commutes with the sigma 2 because sigma 1 sigma 2 is I sigma 3, but sigma 2 sigma 1 is minus I sigma 3. So if I take sigma 1 sigma 2 minus sigma 2 sigma 1, I get 2I sigma 3. Okay. So if they are same, obviously it will be 0. Okay. So otherwise it is. So if they are same, that also answer will come from here. Suppose I is 1, j is equal to 1, will I get 0 from here? Yes, right? Because if the two indices are same, you get 0. Okay. So sigma I sigma j is equal to a commutator of sigma I with the sigma j is nothing 2I into epsilon ijk sigma k. So if I define j I is equal to sigma I by 2, I am just defining because this is basically the j usually angular momentum notation. So later on in your other courses, even this course we will do something about the angular momentum. So you now redefine ji as sigma I divided by 2. So what will be commutator of ji with jj?
I by 2 epsilon ijk is
I by 2?
epsilon
JK,
ijk
epsilon IJK,
Hmm.
JJ.
Is there a 2 here?
Yes, sir.
Oh, sir.
Yes, sir.
Okay. Let us come to one answer whether yes or no, because answers can be only one. Whether 2 is there or not. I just substituted sigma by 2 is equal to ji.
There will be two, sir.
The-
Three is 1 by 4 and the others.
There is a 1 by 4.
Gets cancelled.
So because of 1 by 4, there should be 2? No. Because jk is again sigma I by 2. There is a 2 coming from there. Okay. So that 2 is incorporated. This by 2 is already there in the jk. If it is sigma k, fine. But this is jk. So there is no 2. So any questions?
Sir, what do we call this JNI matrix?
Angular momentum matrices, okay.